Hi everyone, what we've got here is a video that actually comes out of two parts of topic 4. So melting points of metallic lattices is in 4.5 and ionic is 4.1. One of the reasons I've made this video separately is because a lot of the time there are specific multiple choice questions that ask about these melting points. So I just wanted to run through them separately. So before we start, it would be a great idea if you could have a periodic table. And if you're not 100%, maybe go back and check out my videos on 4.5, which is metallic lattices, 4.1, which is ionic lattices, and also the topic 3 revision. Because the topic 3 revision is important because what we're about to do links into periodicity, especially ionic radius. So I'll give you a second to go and grab yourself a periodic table and to double check that you've seen the 4.5, 4.1 and that you're up to date with your periodicity. So let's talk about what holds lattices together. So the really key term that I kept talking about in the 4.whatever videos is this idea of electrostatic attraction. So that is the attraction between two permanently charged particles. So for metallic, it is the attraction between the metal cation and the delocalized electrons. And I'm going to specify delocalized. And in ionic, it is between cations and anions. So hopefully you've got an image in your brains of what those lattices look like. Okay, so the electrostatic attraction between, this is my metallic lattice, between my cations and my delocalized electrons is what holds this lattice together. And here it's the attraction between my positively charged cations and my negatively charged anions. Now, these are both fairly strong attractions, but in general, and this can come up in questions in topic 9, which is redox. In general, an ionic melting point is much greater than a metallic. I make this point because there was an excellent exam question from a few years ago that looked at the electrolysis of molten lead bromide. And it asked students to come to write the full equation for the result of that reaction. That is the creation of bromine gas and lead. But it asked students to put in states, and the states are where people tripped up. There is, in the front of your data book, there is a periodic table with melting points of elements. Oh, and boiling points as well. Excuse me, I've just flicked my pen somewhere. Excuse me a tick while I go and grab that. Okay, so this comes up in topic 9 redox, but it is all about electrostatic attraction. So how do we talk about the magnitudes of those electrostatic attractions? We do it by looking at ionic radius. So if you remember, ionic radius is the distance between the center of my nucleus. So I'm actually going to make this a nucleus. So it's the distance between my nucleus to that outer shell of electrons. So if I've got a small ionic radius versus a big ionic radius, what we are talking about is the distance from this positive charge center to that outer shell of electrons where it's attracting the next ion along in the case of a ionic, or how close it is to attracting the delocalized electrons in the case of a metal. So ionic radius we've discussed in periodicity. If you're not sure about how that trends, please go and check out that video. So there are, and this is something I know I've said to my class in person a number of times, there are two general factors which underlie the trends that we are talking about in periodicity and things like that. It is the distance from nucleus, which is basically the number of shells. And we are looking at the amount of charge. So in an ionic lattice, the strongest lattices are going to have small radius and greater charge. So when I say greater charge, I mean like sodium plus versus magnesium 2 plus. If I'm talking about small radius, I'm talking about sodium versus potassium. If I've got a weaker ionic lattice, I'm talking about a large radius and a smaller charge. So it's all about these same two factors as we've been discussing for a while. It's the distance from the nucleus and the amount of charge on those ions. So, for example, if I've got sodium oxide versus magnesium oxide, sodiums are each a +1, whereas magnesiums are a +2. This is going to be your stronger lattice. This one is going to have a higher melting point. And often when we talk about lattice strengths, we are talking about the melting points of those lattices. So how much energy do I need to put in to overwhelm the electrostatic attraction between the anions and cations in this lattice? It all comes down to how big is my ionic radius and what charge is on that ion. Okay, let's talk about metallic lattice. Now, there are two factors that influence how strong my metallic lattice is, the melting point of that metal. And for our purposes right now, I am largely going to be ignoring weirdo metals like mercury and gallium, because those guys are really exceptions. So in terms of metallic lattices, there are two things that influence metallic lattice strength. That is the metallic ionic radius and the number of delocalized electrons per cation. So the ionic radius and the amount of charge. That is exactly the same two factors that give me my properties of metallic ionic lattices, my apologies. So a hard metal or a high boil, so sorry, I'm going to say high boiling point metal. High melting point, it's going to have a smaller radius and it's going to have more electrons. So that's smaller radius, and in your class, your teacher may have taken pieces of like lithium, sodium, and potassium in the periodicity topic and put them in water to see how they react, to see that periodic trend. You may have noticed, and your teacher may have pointed out, that lithium is quite hard, sodium is a little bit softer, and potassium is softer again. That softness is basically a measure of that electrostatic attraction between, like within that metallic lattice. And as that, as the size of that metallic ion radius increases, that melting point is going to decrease. Additionally, if I have a greater number of electrons, there is going to be greater electrostatic attraction between those metal cations and the delocalized electrons, which is going to increase that melting point. So the takeaways. If you remember nothing else from this video, remember that it is all about ionic radius and amount of charge. As always, I would encourage you to remember the exact terminology, electrostatic attraction. Okay, that brings us to the end of this little video. Thank you so much. If you've got any questions, please leave either a comment for me or you can email amymakesciencevideos, those are with dots in between, @gmail.com. Have a fantastic rest of your day and I will see you next time. Bye.